everyone. My name is Adnan, and today we're going to have a presentation about large language models and embeddings, vector databases, and context. This is a pre-recorded session, so I am not live as I'm probably on vacation right now. But I am coming next week, so for the questions you can send me on Teams or email, and I'll gladly answer them. This presentation will have PowerPoint slides, and also I have created a couple of Jupyter notebooks in Python. So if you don't know how to use a Jupyter notebook, and now it's a good time to see and learn, because it's super easy, and I'll try to explain all of it. And the language is Python, and if you don't program in Python, it should be similar in JavaScript as well. So the tool that I'm going to use is called LangChain, and it has its implementation in Python and TypeScript. So before we start, what are LLMs, large language models? So one of them is ChatGPT. I believe that most of us know that one. And so we all know that now we can talk with it, and we can share some data, we can get something, and so on. How does it work in the background is relatively complex. We're not going to go into that in this session. However, what are we going to do in this session is this. If I ask this ChatGPT, what is my name? It will say that it doesn't have any data about me. So if I say my name is Adi, and if I say again, what is my name? So this time you can see that it has some context from before, and it learned that my name is Adi. And so this is all good, but if we go and click on the new message and I ask again, because it doesn't have the context as before, this time will ask me again and say, yeah, I don't know, so maybe you can provide me. So what's happening here? In the single chat right now, the OpenAI made somehow the context chain so that it remembers the data that you sent before, so it can give you more accurate result later on. So that's all good, but we can see that we're now losing it if we change the chat window and so on. So what happens if we go into the OpenAI API? So they give us the access to their APIs, and if we ask what is my name, it will say I don't know. If we give it and say my name is Adi, what is my name now? It will still say I don't know, because when we call the API directly, it doesn't have any context. So right now, because we are using this web interface of ChatGPT, they made in the background their own context engine. So that's why it works. But if we go directly with the APIs, it won't work. And it's not only this language model. It can be ChatGPT. It can be the GPT-4. It can be Llama or any other. All of them are functioning in some kind of a similar way. So what if we want to give it some kind of a context? So for example, if we would like to, let's say, maybe if you tried sometimes to search something recent inside the ChatGPT, it can say, I'm sorry, my latest training data was like 2 years ago. So that means that, for example, if we are gonna go some code documentation and try to find something, we only have outdated one. But we would really like to get the new one. So in this case, they sold it in some in ChatGPT. They sold it with some kind of a plugin called use the Bing or something like that, and then it actually uses the Bing as a search engine, and then goes and scrapes the page, and then tries to get some data from it, and it gives you the data back. That was that is in the beta, and recently it didn't work. Now they put it back and so on. But then again, they built it inside this, and if we want to use the APIs or any other open source tool, we will still have the same problem with the context and with the lack of modern data and so on. So basically, the LLM can only show you what it was trained on. In order for us to give it more information, then we have to fine-tune it and train it more and more and more. So that means that theoretically we are never able to get the real-time data because of it. So what can we do then in order to get the real-time data from the database, let's say, or if we want to go to some external APIs and so on? So luckily there's a really popular tool for that, and it's called LangChain. So that is our subject for today, and I'm gonna present that today. So LangChain is an open source tool, and it is, as I said, it's in a Python and TypeScript, available in both platforms and languages. And it is focused on composition and modularity. So what do those things mean? Composition and modularity. It means that it has many different components. So it has components, for example, for prompts. It has components for different type of models. In this case, it has like 20 plus integrations with the ChatGPT, with the Llama and others. It also has tools for indexes. So how to load documents, how to splice those the texts, and how to convert them into embeddings and the vectors, and how to connect to some vector databases, and how to retrieve it. So today our focus will be mostly onto the how to load the documents, how to split the text and keep the context and not to break it, how to save it into vector stores, and what are the vector databases in general, and how to retrieve the data. Other than that, I'm going to show some other cool things as well, like we can show some chains and some agents, and it will be more clear when I start showing it in a demo session. This technique is called Retrieval Augmented Generation, and shortened RAG, and basically it consists of document loading, splitting, storage, retrieval, and output, and that's what we're gonna do today. So what does it mean, document loading? Document loading basically tries to access some specific website or some specific file type or whatever, and then it converts it into something readable for LangChain. In this case, it returns the document object. And as you can see here from what I wrote, it can access the websites, databases, YouTube, whatever it has connector for. But it can also access PDFs, HTML, JSONs, and so on. So the question is, why would we load, let's say, the YouTube? What would be the purpose of that one? Let's say that we can load a YouTube and transcribe it and get the text and summarize it. And instead of watching half an hour video, we can summarize it in 2-minute text. So let's say that would be one of the options. Let's say the PDF would be that in CGI we have the handbook and the employer's handbook, and there's many things explained inside there. So every time you want to do something, you would need to open the PDF and go and search and try to find it. But you can actually then feed this PDF into your large language model and ask anything you want about the PDF. And the system will be smart enough to find that text inside that PDF and feed it inside the LLM. The LLM then will actually understand it and pack it nicely, and it will give you an answer. And so on. The databases and some different APIs and so on that you can actually get data and then it's mostly you'll get the document object which is non-readable, and then the LLM will be used to actually understand it, pack it nicely, and then chain it in for the context so that you can ask multiple questions and so on. So here you can see that we have many document loaders. So what can we load here is some of the most popular ones from the YouTube and the ArchiveX and the Wikipedia, which are unstructured and the public, and then some proprietary, which are some chat applications like Telegram and so on, and also from the data stores like a Google Cloud, Amazon, Azure, and so on. So basically, we are covered out of the box for most of the things that we need. The LangChain is very maintained open source project on the GitHub. It's, I believe, in one of the top 10 of most maintained and contributed projects right now. And it's also used in many popular cloud platforms like Azure and Google and so on already to help work with the LLMs and so on. So we can go and show that in the real time. So this is a Jupyter notebook, and this will be available on the GitHub page. And I have divided them into multiple files and notebooks, and this one will work only with the document loading. So I just gonna explain a little bit. So document loading is basically loading from the URL API, PDF, database, or whatever, and then it converts it into a document file. Then document file needs to be split into something smaller chunks. The problem with those splittings is that if you have let's say that a book of 300 pages, how would you split the book? If you go and say split by 500 characters, then you would be able to break in the middle of the sentence or the word. If you say split based on the 10 sentences, then you would be able to break the context of the text itself. So that's also not an option. And then if you would ask something about that, you would maybe get only the first paragraph or something like that, and that's not what you want. You want the whole thing that you're interested in. So the splitting has to be meaningful, and the splitting has to be semantical. So we're going to show that a little bit later. And then we have to save that into a vector database. Vector databases are different than the relational or non-relational databases, and they are multidimensional, and they save semantically. So that means that similar things will be saved in the similar places, so that those LLMs can get that kind of a data relatively quickly, much faster than the regular databases. And then when we want to do the retrieval, we're going to go and query that vector database, and then we're going to get those splits and chunks and the ones that are relevant to us, and then we can create a prompt with those chunks, and then we can pass that to an LLM, and then we can get the answer. Why do we do this? The reason is that all the LLMs have limitations. So if you have a book of 300 pages, you can't feed the 300 pages to the LLM because it's a limit on tokens. And also it can be relatively expensive The more tokens you send, the more money you have to pay, the more processing has to be done, and so on. So you only want to send the minimum amount of data to get as fast as possible, as cheap as possible, and the only thing you need. So that is what LangChain does really good. So let's first focus on the document loading. So before you can use this, you have to install the LangChain, and the pip is a package manager for Python, so it should be fairly straightforward to install it. The same thing would be for the JavaScript. You would do the maybe npm install LangChain, and then you would do the same thing. So those are some generic things, and I have created an open API. I have OpenAI key, API key, and I have created an env file, and that's where I load my key. So when you download this from the GitHub, if you download it, it's important to create that env file and have this variable name, and then add it your actual key. So let's run this. So now we imported all the necessary packages and so on, and we have loaded the API key. So the next step here will be that we're gonna use the LangChain document loader, and we will import a PDF file. So in this PDF file here, this is a book that I found, open source book for some project management and so on. And when we load that book, we are gonna assign it to pages. So we can run this, and you have to understand that each page is a document, and that document has some kind of a page content and some metadata. So if we run this len, we will see here that we have 274 pages right now from this PDF. And if we do this, we can say that from the first page, and to give us the first 500 characters, this is basically what it will give us. And so that means that we have successfully loaded this page and this document, and divided it inside the pages. Hence, we can access it like this. This is the first page inside all of the pages object, and we can also see the metadata of it. And the metadata is, this is the source, it comes from here, and we are on the page 0. That means the first page. So it's, as you can see, it's super simple to load the PDF document. And of course, this does nothing except loading it. But in later in this session, we're gonna start chunking this and splitting it, and then saving it, and then we can use it. Just before we continue, I would like to show something from the YouTube. So we can download basically the YouTube. We can use some other AI tools. In this case, we can use a generic loader to load the YouTube video. But before that, we have to download, and then we have to convert it into a video file, and then we have to convert it into an audio file, which will be sent to the OpenAI Whisper parser. That parser is gonna basically give us back the text from that video. We're gonna then load that, and we're gonna show it here. So those are some of the packages that you have to install. And here, as you can see, this is in LangChain already has the YouTube audio loader, and this is OpenAI Whisper parser. That is the AI provided by the OpenAI to transcribe audio into text. So if we run this one here, it should download the video, it should convert it, and so on. And you can see here that it's some lecture from Stanford about the machine learning and by this professor. And this is the format M4A. and it's already downloaded, and this is the size of it. And now we are gonna extract the audio from it. And when we extracted audio, we are gonna transcribe all of this. So this will take a couple of minutes. It's done, and we have run, we transcribed everything, and we are getting the first 500. And as you can see here, it has some formatting issues and so on, but we can say that it has in the first part of the video, it has something with the automate any workflow and find the fixed vulnerabilities and so on. Of course, we can clean this and make it nicer, but for the demo purposes today, this is more than enough to show that we can actually download those videos and get them into a document file. The same thing we can do here, and we can use the web-based loader. And I found one MD on the GitHub, and then we can load that one, and then we can show the page content. And this has as well as before some formatting issues and so on. But we're gonna solve all of those later, and I'm gonna show you how. But as you can see, we have loaded them all in and made a doc from it, and now we can start splitting it. The next step is to split those documents, and there are many different splitters that we can use, and some of those are based on the character splitting, markdown, header splitting, token splitting, sentences splitting, and so on. So we're gonna show some of those here in this Jupyter notebook, and we're gonna see how do they work, and what are their advantages, disadvantages, where should they be used, and so on. So in this first, let's import all of the necessary packages, and here we're gonna work with two components, that is recursive character text splitter and character text splitter. So we're gonna import those, and for the just for the test right now, we're gonna use the chunk size 26 and chunk overlap 4. So what does it mean, chunk size and chunk overlap? So basically, we're gonna tell to the system how many of the characters we would like to have in one chunk, and chunk overlap would be something that is in between two different chunks. So you have chunk 1, chunk 2, and chunk overlap would be like 4 characters in between those two. Of course, those are really small number, so they don't work and make anything meaningful, but they're good for showcasing and how do they work. So we're gonna run this one as well. So here we're gonna just run this recursive splitter and this character text splitter. One will be called R splitter and one will be C splitter. So we're gonna import those two, and we're gonna check first with this string here from A to Z. We're gonna load that one, and we're gonna use this recursive character text splitter, and let's see what will happen. So we see right now that we basically have one string which is not split, and basically the reason for it is that the chunk size is 26 and this is less characters than 26, so it did nothing. But if we add more than 26 characters, and if we load that and we try it now, we can see now that it has two strings, one that has this amount, 26 of the characters, and then this one with a smaller. However, you can see that this one ends with a WXYZ, and then it starts with the same one, and it's 4. So this is that chunk overlap. So we didn't want to chunk it in just like slash it in 2 pieces. We actually wanted to leave a little bit of a context in for the both chunks. So What about this one? So if we go with the R splitter, which is a recursive one, we're gonna get now the three parts, three strings. This is much more complex string because it has these empty spaces in between. But if we go with this character splitter, we're gonna get the same. The reason for that is that we need to provide it with a separator. So in this piece of code here, if we add a separator to be an empty space and then run this splitter, we're gonna get now something more meaningful, because now it will know actually that the empty space is something to look at, that's something that can be used to divide the strings. And now in this case, it divided onto three pieces. So of course this means nothing, but it shows how they work and how they group and so on. But let's see this on something more realistic, like this text here, for example. So the length of this text is 496 characters. So now we're gonna increase this chunk size to be 450 and without overlap. But we are gonna leave this recursive one, the character one as is. We're just gonna use the empty spaces to divide. And in this recursive one, we're gonna use these next rows. So basically, like if there's anything that has double row, like two paragraph separate or something like that, that will be the first one to divide as a higher priority. If you don't find any of those, then just the next row, and then the empty space, and then basically any character. So if we load this one here, and then we try with the character splitting, we can see here that we have this array and two strings. And here we can see that this string here was literally cut off here. So sentences have a period at the end, but also, and then it ends, and then the new string is have space and blah blah blah. So this doesn't look that good. Like, we don't want this. We don't want to cut off in the middle of the sentence. So let's try the same thing, but now with the recursive one. So the recursive one, because now that one is dividing based on the maybe the paragraphs, and trying to understand that, yeah, maybe those were two different contexts if you have divided them by two rows and so on. So if you do that, then automatically you get something more meaningful, which actually now divided into two strings, and both of the strings are their own thing. So here we are separating them in smaller chunks. If we run this one here, and we can see now that sentences are divided into smaller ones, and here you can see that this comma is basically used in order to separate some of the sentences. Hence, the new strings start after the comma and so on. In case that sometimes you would divide and have the new string starts with a dot and so on, then you would use these regex, and then you would actually prevent new to start with the dot, but it should end with a dot and so on. So let's now take a look at this book that we already imported before, and let's run this one here. And here we're gonna only use the separator that is just a new row, and the chunk size of 1000 and chunk overlap of 150, and this length function here is by the default. So if we do this one here, and then if we split the documents, if we run this to see how many documents do we have 603, but if we take a look at the pages, we can see that we have in this PDF 274 pages. So basically, if we created from 274 pages, we created 603 documents that we can now use to store into the database, and later use it with our large language model. So that is one way of doing things. Using those different methods. But another one is that token splitting. So tokens are often 4 characters. So what is the difference between the token and the word or character? And let's see here. So we're gonna import this token text splitter. And we're gonna just, for the sake of this test, we're gonna write the chunk size to be 1 and the chunk overlap to be 0. And so here, if we just load it and add this text here, and we can see now that that this is divided into something smaller, like a foo, bar, and so on, and it divided them into tokens. Which all of them are less than 4 and so on. So it's not a pure character, but it's more like a set of characters and so on. So if we increase the chunk size and load the same thing, and load the pages from our book, we can see here that the token, the difference between the character, the other methods that are using recursion and the character splitting, is that when you use the tokens, then you always get the metadata as well. So here what we did was we used this text splitter token one, and basically we just provided it with the pages that we imported from that PDF and converted into pages, and then we took the first page here and from the document, and we can see here the metadata has this source that comes from here that we are on the page 0. And this is for the whole document. And to see that what they do, when you use a token one, even when it splits the document into smaller tokens, it always persists with the metadata on every chunk. So why is that good? For example, if you have a PDF and you would like to maybe ask a question and use it as a and then like have a reference, like where exactly is it? What is the part of a document? And maybe give me like if you have like hundreds of documents and PDFs and so on, you want to keep that metadata to tell you, okay, from that document, from that page, from that paragraph, and so on. So now if we go into the first page of the document, we can see that we have this metadata exactly the same as here, where it says source and page, first page, and so on. So of course this can be improved in the sense that we can get more and attach more of the metadata information. So now if we want to do a little bit more with, for example, some other types of text like empty and markdown, we can let's say we can do some markdown. We can use this component called markdown header text splitter, and because we know how that the markdown files or empty files are standardized, then we can use something like some kind of a rules on what to split on header, which is like 1 hash, 2 hashes, 3, and so on. So let's import these, and here we have this text, which is some kind of a markdown document, and we load that one, and we say, okay, split this into by the headers basically, and then import it here and load it, and then we want to see the split one, and the split one will say, okay, hi, this is Jim. And basically it came from here, from this basically first chapter, and it knows what to distinguish between the headers 1, 2, 3, and so on. And as you can see here, it keeps the metadata, it basically adds that it's from the title, and there's a header too called chapter 1, and both of those came from here. So if we go to the next chunk, we can see here that hi, this is Lance, and that is basically this part, the second part here. And now in metadata we have the header that is actually title, chapter 1, and this is this is the section. So the more you go and the more you have the bigger document, the more metadata will be preserved, so that you can always pinpoint exactly where does it come from. So this is our document splitting. So we had the document loading, and now we have split it into smaller chunks. And the next step is to save this into the vector database. We're at the part of the storage, the third part. It's a third Jupyter notebook now. So now we're gonna take these splits, chunks, and we're gonna save them into the vector store. So let's load our packages, and for this purpose here, in my documents folder, I have multiple PDF files that I'm gonna load right now. And intentionally I left here a duplicate, so that we have lecture 1 repeating itself, and then lecture 2 and 3. Just to show some disadvantages of semantic search. So we can load all of this, and we can use this recursive character text splitter with a chunk size of 1500 and the overlap of 150. And if we load this now and we split it, and then we check how many of those documents we have 209 based from all of these PDFs here. So we now need to create embeddings. So what are those? Basically, before we can save into the vector database, we have to convert them into vectors. So when we take something like some kind of a sentence, and if that sentence is let's say related to the pets versus the cars, when we start converting them, those vectors will be more similar to each other if they're pets, like a dog and a cat, than to a car. So if we were to then compare those vectors, we would see some numbers showing up, and the higher the number, the better the probability that they are similar is, and then we can safely return that as something that we searched for. So right now we're gonna import the OpenAI embeddings, and we are gonna use those. And before we continue on those PDFs, let's just have a small test here. So here we have three sentences. I like dogs. I like canines, and the weather is ugly outside. If we load this and we create embeddings from them, and then we can use this NumPy. It's a Python library for numbers and so on, and some mathematical calculations. And if we use this, if you ever saw this np dot, if you haven't, doesn't matter, it will give us a number, and the higher the number, the better it is. So if we were to compare the embedding 1 and embedding 2, so basically the dogs, so basically animals in this sense, and we run this one here, we would get this number here, which is relatively close, almost 1. But if we were to compare the sentence 1 to sentence 3, so here is about the weather and this one is about the dog, and see the similarity, we get less similar than this one. And if we compare again the sentence 2 with the sentence 3, we can see that again we are getting some lower number, and of course we can now safely say that the sentence 1 and sentence 2 are more similar to each other. So what we're gonna do right now is we're gonna install one vector database called ChromaDB, which is open source and something that I recommend. It's really good. And I already installed it, so I'm just gonna import it. And here, this is the name of the directory to persist, so that we can use this database later as well. And just in case for some leftovers, we don't want to have some bugs, we're just going to remove what I created before for testing. And here we're going to create this vector DB. We're going to add those splits and embeddings, and as well the persist directory, so that we can use it later. So if we run this here, and now if we take this collection and see how many of those embeddings we have, it's numbers 209. So now we have those embeddings, and we have saved them into a database. So now we would like to go and ask the database to give us something meaningful, and so on. So let's say that now we're gonna go back to those PDF files, and in those PDF files they were about machine learning and so on. So I would like to ask, those were the lectures, so who can I ask to help me if I get stuck, and so on. And does that kind of information exist at all in those documents? So this is the question string, and now we are gonna go and we're gonna try this similarity search with this question, and this K is basically how many documents we would like to involve and get returned. So we're gonna run this one here, and how many documents we got? 3, of course, because we asked for 3. And if we go here and if we check that now the first document that we got back and its content, we can see here that when we asked about the email, we actually got a chunk from the database that actually starts with this email. So and then of course it gives us something more that maybe we're not interested in now, but then again, that's the chunk we got, and it actually contains this email here. And let's just save this for later use. So this looks good, because obviously now only by using the vector databases and just chunking and saving some texts and documents inside it already gives us a lot of power, where we can literally ask the database, and that database will give us something through semantics. So that's really good, but then again it has its problems. So let's address some of those problems. So for example, here let's ask about a question about a MATLAB, and in this case let's return 5 documents, and if we were to run this document here and this document here, they are basically the same. Because both of them contain this MATLAB, but actually they're the same document, but we just duplicated them here when we imported them. So just because we haven't we duplicated them and we haven't cleaned or did anything, now the system thinks they're 2 different files, and of course you're gonna get 2 documents. And now the problem occurs is if you take these documents and then you send it to LLM with so many tokens, then this will be like unnecessary and too expensive to send. So we don't want that. Of course, I'm gonna show some ways how to actually fix this. But this is one of the failures, and showing that this is good but not perfect in any way. So here, for example, there's another failure mode that I can show, and we're going to ask about the regression in the 3rd lecture. And if we go here and again, let's get 5 documents and see what documents did we got. We mentioned in the 3rd lecture, but we actually got the 2nd one as well, and we are not interested in the 2nd one. Basically it included something that we haven't asked for, just because it had a regression in itself. And if we check it, we can find here that there was a regression somewhere, yeah, in the file, and so on. So we see now that these vector databases and the semantic search are really good, but we can address some of those issues and make them even better. Hi, so this is our 4th part, and it's a retrieval part. And so now we learned how to load the documents, how to split those documents, how to save them into a vector database, and now we're going to learn about how to retrieve those from the database. So there are multiple ways of accessing the data, and some of them have their advantages and disadvantages. There are also ways that we can retrieve the data without the vector database and the vector database. So today we're gonna focus mostly on two ways. That is maximal marginal relevance and LLM-aided retrieval. So what are those? So this MMR, or maximum marginal relevance, is basically, if we take a look at this example here, the first two sentences are: Amanita has a large and imposing epigynous fruiting body, and a mushroom with a large fruiting body is Amanita. So those are very, very similar. But there are many times that we don't want to have most similar responses together. Sometimes we would like to have something that can fill the whole context. So for example, those two sentences, the first one and the second one, are basically the same, just rephrased differently. But the third one actually is talking about a mushroom that is poisonous. So maybe that is something that we don't want to skip. We would like to include that as well. But then again, we would like to filter the first two so that we don't have multiplication and overflow of data. So this MMR comes really handy. And we're gonna show the example how does it work. And the second one is this LLM-aided retrieval. So basically, sometimes we want to get some data, for example, from a database, but it's not just purely a question that we can just search based on some similarity or semantics. We would like also maybe to do some filtering before we get some data. So for example, here we have a database of for example, IMDb, and we are asking questions about alien films made in the 80s. And what we can do here is we can use the large language model, and we can take the context out of this sentence, and we can create actual search term or a question, and then we can create also a metadata that can be used for filtering and so on. So in this case, the LLM is going to make a filter that is a year and 80s, and it's going to make a search term that's based on aliens. So let's show that in an example. Jupyter notebook and the fourth module, and what we're going to show now is different ways of retrieving. So let's first import what we need here, and of course it's important to install the Lark here. Let's load our database, and let's see how many documents do we have in database. We have 2,209. So now here we have the text that we had already mentioned inside the slides about those mushrooms. So let's load that as well. Let's add it to our database, and let's now ask a question to our database regarding all white mushrooms with large fruiting bodies. So let's load that question, and now we are going to use a similarity search, the one that we already used, and let's see what will it return. So here it returned a mushroom with a large fruiting body, and again a large fruiting body. So basically we got that what's similar, but that's something that we don't want. So we would rather have something that is relevant to each other, and it gives us a little bit more information. So in this case, again, we want to have two documents, but include all three of them. So if we run this one here, now we can see that it basically gave us the first sentence, skipped the second one, and then it gave us the one with the most poisonous, which is in this case maybe more relevant, and that's something that we wanted. So let's see now we have all of those files that we uploaded before in those PDFs. So let's now ask the same question as before about the MATLAB. So if we run this one here, and in this case, we are gonna go with the first document and the first few hundred strings. And here we see that we use similarity search, and we asked about the MATLAB, and we got this answer here. And if we ask again from the second one, basically we got the same answer again. And remember that we uploaded that file, the same file, we duplicated it 2 times. So the system doesn't know and actually gives us the same thing again. But maybe that's not something we want. We want something from some other page and so on. So let's see now the difference in between if we use the MMR and if we do the same thing here. We load it and then we show, and of course we get the same response as before from the page 1. And if we go next one, now we're getting something different that is maybe more relevant or to that MATLAB question. And not only more relevant, but something that actually fills the gap and adds a little bit more context to it. As you can see, it's better to use the MMR than just similarity search. So here, what we can do is this. When we work with the metadata, we can do that as well. And so, for example, here we can ask a question. What did they say about regression in third lecture? And then we can also ask a question and how many documents, and then we can add a filter to it. So if we do this and then we print this, we can see that this document, that we would get like some kind of a text, was actually from the page 0, page 14, page 4, from the lecture 3, because we added that filter. So this is good when we want to add some filter, because we know already what documents are inside. But if we don't know those, then it would be really good if somehow we can make this filter automatically. Hence, we can use then LLM actually to make a filter for us. So here we import OpenAI, and then we can have this self-query retriever and this attribute info. So if we import those, and here we're going to make this kind of some kind of a metadata, and what we don't want to have, and this is like for the source, this is for the page, description here like about the documents and the type, and the more we add here, the more we explain, the easier it will be when we inject this into the LLM to understand what we want and give us what we need. So if we add this one, and now we load that, and if we have now, we create a question now. What did they say about regression in third lecture? Again, and if we now go to the documents and try to get the relevant documents with that question there, we should send this now request to the LLM and for the processing. And if we now print that, we can see now that even without us mentioning anything about the lecture 3, it found out and that this should belong to the third lecture, and made a filter for us, and then basically gave us the answer and the filter together. So that's something that we can use the LLM. So this asks question like, okay, so we are retrieving this in order to send this to LLM, but somehow now we're using the LLM. So we're double using LLM, and the answer is yes. We're sending more requests to LLM, but this will give us a little bit more precision than actually if we just semantically search it through the similarity or MMR and then just feed it into the LLM. This is much more optimized. And there are also like compression. So basically we can get many different responses, but maybe we are not interested in all of them and it's too big text and so on. So we would like to filter it a little bit. And then we can use again the document compressor, this one here. and this LLM chain extractor and contextual compression retriever. So if we load those two, and here we can we set some parameters, and so we're gonna wrap our store. We're gonna use this retriever, and now we're gonna ask the question, what did it say about the MATLAB? And if we run this one here, we're gonna ignore these error warnings. And basically what we got here is we got really a structured answer with a document 1, document 2, document 3, document 4, and so on. And one thing maybe some of you have noticed, and is that this document and this document are the same, and we don't want that. And then this one and this one is the same. So we would rather include the MMR than the similarity search in order to get something that's not repeating itself and so on. So let's do the same thing. We're just gonna add this search type to be MMR instead of the similarity search. And if we ask now the question, now we're getting only 2 documents. So basically there's no more repeating. So it knows that those 2 are almost the same, and there's no purpose in giving us the same answer multiple times. So it just gives us those ones that are a little bit more different but relevant to each other. And there are some other ways of retrieving and without even using the vector databases. So 2 of them are let's say SMR retriever, SMM retriever, and the TFIDF. Whoever worked with the machine learning may recognize these, but it's irrelevant for this session. So we're just gonna import those. We're gonna import this document. So right now we're importing directly from the machine, and now we can retrieve it. And if we ask a question, what are the major topics for this class? And if we run this one here, we can see here that we got this document with some text inside it. And if we run the other one, we get to see some other, and maybe the first one is a little bit better than the second one, and vice versa, and so on. But this is now basically there's like X amount of these different options, and then in order to get what you want, you would need to go through all of them and somehow test it. And but the good thing is that we have them; they're already built. They're relatively good enough. We just have to pick the correct one. And if we don't want to do it like that, we want to save it more permanently inside some kind of a database and have it more manipulated. Then we go through those vectors and use those other techniques that I mentioned above. Our 5th part, it's about the question answering. So in a nutshell, what do we do here is we have a question, we send it to a store, we get the relevant splits, we set that as a system prompt, we send it together with the question to the LLM, and we get the answer. So what happens is that if we, for example, have a huge database or hundreds or thousands of files that may be relevant to answering your question, then if you were to send them all at once, what would happen is that the LLM would not be able to handle them all at the same time. So there are some methods that we can use in order to divide those and process them and so on. So there's like a map, reduce, refine, re-rank, and so on. So we're going to mention, then I'm going to show something with the map, reduce, and refine. So map reduce is where we send every chunk separately to the LLM, like a separate question, and then we can have them in a really small chunks and then combined, and then we can get the answer. The advantages of this one is that if you have a lot of smaller things that are independent, this will work great. The problem is that if you have something that is maybe chunked into multiple ones, but it's the same context, they all relate to each other, then there will be a problem, because then we are basically asking the questions and getting the answers based only on one without knowing the others. So it can give us some kind of incomplete answers. So there are some other ways, like refine, where we actually are sending the request with this first chunk, and then we're getting the answer. We are like a little bit fine-tuning it and sending it again and again, and fine-tuning it again, and so on, until we get to the point where we have the ultimate complete question, perfectly fine-tuned, and then we send it to LLM and we get the final answer. And the re-rank, for example, works a little bit more on probabilities, and then selecting the highest scores of what is the most relevant to, and then sends that one, and so on. And there are many others. So let me show you. So we're on this part here of the output. So let's load our environment variables. Here we're using the OpenAI's GPT 3.5 Turbo. You can use any you want. So we're going to load our database. We're going to check that, yes, we still have the same number of documents as before. So we're going to do the similarity search and ask what are the major topics for this class. So it gives us the answer 3. So let's then load the LLM itself, and this is the LLM name, and which is a GPT 2.5, and the temperature is something interesting to look after, but the temperature 0 means our most accurate answer. So let's load that as well, and let's load this chain, Retrieval QA. Let's load the LLM and the vector database, and let's create a chain, and with our question, which is what are the topics for this, and we ran that one, and then if we run this one, then we have the major topics for this class of machine learning and its various applications. So now you can see the difference in between the just similarity search, which actually gives us number 3, and then if we feed that into the LLM to little bit fine-tune it, then we get something that is much better. So now we can even go a step further, and we can create prompts. Like in this case, we're going to create a template. Use this following piece of context to answer the question. At the end, if you don't know the answer, just say you don't know, don't try to make up the answers, use 3 sentences maximum and keep it concise, and always say thanks for asking at the end of the answer. So we're basically saying to the LLM, giving instructions and giving like setting a context here, and we're gonna set the question and so on. So if we load this one and we run this chain, now we can ask the question, is probability a class topic? So now if we go into the result and we print the result, the answer will be yes, probability is a topic that will be covered in the class. Thanks for asking. So now we're getting something a little bit more fine-tuned than before, and actually adds this thanks for asking because we said it to do it. And if we go inside the document itself, we can see what we have here, and that is basically the answer, where it come from, where it basically what it sent to LLM, and then LLM actually took this piece of text, understood it, that this is actually that there's like a probability inside this text here, and then it said, yeah, I found a probability, and it looks like it's covered in here. And also we can see where it found it in the first lecture here. So we can do it a little bit more, but now instead of using, now we can use this map reduce here, and we can send it, and we can check for the results. And here we can see that based on the provided information, it's not clear whether probability is a specific topic covered in the class. And this means that the map reduce, for example, in this case, maybe has split them in a way where it wasn't clear enough when we were sending that to LLM. So LLM couldn't get it, and then it basically just give us the answer based on what it got and try to understand. Hence, we can then replace this with some other chain types, and where we can find something more that fits our needs. And also, even if we have those chains right now, and if we run something like we run the database again, and we ask, is a probability a class topic? And it will say, yes, probability is a topic that will be covered in this class. So we get the same result as before. And we can ask now, what are the prerequisites? If we run this one here, we will get the answer. And it says, our prerequisites are needed because they provide financial knowledge and skills, blah, blah, blah. But this is this may not be something that we actually asked, because here it's saying that understand the concept and so on, talks about the machine learning itself, not about probability. So that means that this chain here does know nothing about this one here. So we need to introduce the memory into this, so that it can keep the context no matter how many questions we ask, and no matter what we ask. So let's see that as well. Our last slide, this is our last notebook, and here we are going to connect everything we learned today, and we're gonna make an actual chat application. So just to show what we ended up last time was to show how the memory works. So let's just run all of our environment variables and imports, and let's run the GPT, let's run the database, and let's just check that everything works. Yes, so based on the similarity search, let's check that LLM works. Good. And let's just check that we can ask a question as before, and yes, it will give us a probability, and thanks for asking, and so on. So we already covered all of this. So now we're gonna add here a memory key that will be like a chat history, and we're gonna add this long chain memory conversation buffer memory. So let's load that one, and we're gonna load the LLM, the retriever, and the memory. So now we're going to ask the same question. Is a probability class topic? And let's print the answer. Yes, probability is a topic that will be covered in this class. So that's the answer we already got. But then we asked a question about prerequisites, and it just gave us some vague general computer science answer. So let's try it again. And we hope that this time it will know that we actually asked about the probability, and it should have some context with it. So if we give an answer here, then we get this answer, and here we can say to understanding applying statistical probabilistic methods. So this part now, this question and this answer they know that this was the question and this was the answer, and because we saved them in the memory. So basically what we did right now is that we have the document loading, document splitting, saving them in the database, retrieving them from the database, and we added as well as memory into it. And now we have a fully fledged a chatbot application that can read any file, any website, any video, or whatever we need. So in order to show that all, let's have some small simple demo that we're gonna run. So here we import everything we imported before. Here we are gonna load this database, we're gonna load this PDF loader, we're gonna do this, split the documents with this text splitter, we're gonna create the embeddings, we're gonna create a database, we're gonna define the retriever and the search type, and we're gonna create a chain here. However, here we haven't added a memory because we're gonna inject the memory in another way. So let's add this. So here, what we're gonna do is we're gonna, on every question that we ask, we will provide with the question the question and the answer from the previous one. So that basically then through the whole chat, it will know and what was happening before. So if we run this one here, and if we now create a GUI for it, our GUI, and we can talk with this file, machine learning lecture 1. So if we go into that file, we can see that there's an instructor, Andrew, and that he's been working for 15 years and so on. So let's ask a question about that. Who is the instructor? The instructor is Andrew Engame. Good. What is he working? So this is good because we asked who is the instructor, the system knows that he is instructor, and then we asked, yeah, what is he doing, without providing more context to it. We didn't say, what does the Andrew work? We just said, what is he working? And the system was smart enough because it had memory that we talked about the Andrew, and it says that he's working on machine learning, which he actually is. I personally work in machine learning, and now we created our working chatbot that is almost the same as a ChatGPT chatbot. And we combined all of those things together, and as you can see, most of this code here and this code here is basically just to make the GUI, but this is all we needed to load together with those imports here to create this app. So now at the end you can see that it's not hard to make it. It's literally a copy paste of this, and you will have a fully functional chatbot that can have the whole knowledge of your database, your APIs, documentation, handbooks, and so on. So we are going to finalize now this session. I hope you learned something new, because this is a pre-recorded session. I won't be able to answer your questions, but when I come back, feel free to find me in the office and ask me anything. And based on this, what I showed right now, we're going to start a new project in our AI group, that we're going to use the LangChain and the large language models in order to communicate with GitLab and try to get information to the API, and basically allow the project managers to make better decisions for the teams based on the data that they ask the AI. So thank you, and have a good one.